Hello, welcome back to the physics classroom. Today I'm talking about work and heat. So some of you may head to work each day. Some of you may get really hot at work. Are they related? Are they similar? Now when I talk about work, I'm pretty much talking about mechanical work of some kind. So work is a product of a force over a distance. So we're applying a force, say lifting a pen over a distance. I've done some work to lift the pen. I'm going to throw a ball over a distance. And it's going to move a certain distance doing work. Work is measured in joules after this guy, James Joule. Now he found that when you move water through a paddle, the water starts to heat up. So the mechanical work, mechanical energy converts to heat energy. Likewise, maybe you'll become a mechanical engineer and you'll work with combustion engines. The heat applied to the engine is converted to work, converted to mechanical energy. So this is really important and really vital in today's lesson. And I've pretty much summed it up here. Work and heat are two sides of the same thing. An object can be heated using mechanical energy, and heat can be used to do work. So now we have to look at some symbols when it comes to work. So internal energy of an object is given by a capital U, and it's the total potential and kinetic energy of the particles within the object. This may be familiar to you if you've done science before. There's also Q, which is the heat energy, thermal energy. We've also got W for work, and doing work on an object will increase the internal energy, or an object doing work, you'll lose the internal energy, the internal potential kinetic energy. So I want you to think about this further. Maybe you own a basketball or some sort of football or something, and you want to pump up the ball. So you've applied a work, you've applied a force over a distance, and what would happen to that pump after you've finished? If you put your hands around the pump, it would feel hot. So the work applied, like I said before, the mechanical work, the mechanical energy has converted to heat energy. And this relates to our first law of thermodynamics. And this is a change in internal energy of a system is equal to the heat added to it, plus the work done to it. So heat, work is equal to the change in internal energy. And you could do the reverse of this. The work done by it, or the heat lost from it, is equal to the internal energy lost. So we have this rule. This is like the mathematical version of that. The change in internal energy is equal to the final internal energy minus the initial. And you can see the subscripts there. So U, internal energy, subscript F for final, minus U, internal energy, subscript I. So it's purely just the change in internal energy, and it's equal to Q, heat, plus W, work. And we can also put it in a diagram like this. So you've got work going in, work going out, heat going in, heat going out. And this is the change in internal energy of the system. So we can apply this to different scenarios. Let's do an example. You can see a table. We want to try and fill the table out. We know change in U is equal to UF minus UI. So we know this is 32, that is 50, and we don't know UI. So we can figure it out. So rearrange this. You have UI equals 50 minus 32, which which is 18. Now, we need some units. It doesn't give any units in the table, but I forgot to highlight this before. Because of that man, that scientist James Joule, work energy is in joules because of his discovery of the conversion of mechanical energy to heat energy. Alright, so you may also remember the change in internal energy is equal to the heat plus the work. So we know the change is 32. We don't know the heat added. We know the work is 10. So the heat added is 32 minus 10. So before I go through an example, just notice the direction of work and heat. So work done on the system is positive. Work done by the system is negative. It's leaving. This is entering. Heat added is entering, it's positive. Heat removed is negative. Alright, so now we have a second example. We've got a pump full of gas. It's allowed to expand, and 80 kilojoules of work is done by the gas on an object. So this is very important. 80 kilojoules of work is done by the gas. So that's our first thing, 80 kilojoules. And it's done by the gas, so it's negative. Remembering our diagram from before. Work done by the system is going out, so it's negative. Heat added is going in, it's positive. Alright, next, the gas is warmed by an addition of heat energy. So this is heat being added, so it's positive. The last thing, if the initial internal energy is 500 kilojoules, what's the final internal energy? So what's UF? So we know our rule. That's our rule for internal energy, work, heat. Sub everything in, rearrange. Our final is 500, so add 500 to both sides, minus 80 plus 100. So it started with 500, it took away 80, because that's the work that it did, and it added 100 joules, or kilojoules, sorry. So it ended up with 520 kilojoules of energy still in the system. So that was its final internal energy. A heat engine is a great example of how a system with thermal energy can work. So there's many types of heat engines, and further along the physics, you'll look at more complicated engines. So a heat engine is something that gets heat or a high temperature source and converts that energy into work. And that's the whole point of the heat engine, converting the heat into work. It rejects the remaining water heat to a low temperature sink. This equation here is quite important. So the heat in is equal to the heat out, QC, plus the work done. So if the heat in was 100 joules, the heat out was 20, you can figure out the work done. So it would be 80 joules. So we can also look at the efficiency of this engine. So we need the work out, that's the energy output, over the energy input. So this down here is wasted energy. That's what's gone into our cold reserve. That's energy that goes out that's wasted. So the energy output is just this work done by the engine. 80 out of 100 joules, that was useful. So 80% efficiency for this heat engine that I made up. And that's how you calculate the efficiency of a heat engine.